guess we're meant to be. Maybe if we wanted more than conveniently.
Welcome, ladies and gentlemen, to the Nobel Prize information event. I'd like to thank all of you for coming, as well as the University of San Francisco for their commitment to education. I'd also like to thank the many people who helped with this event, including Margot Fry and her team, Valerie Gonzalez, Francisco Gomez, the U.S. film crew, and the deans of the business school. And of course, the students for coming today. Thanks very much. We have some really exciting speakers today, and there are professors from UC Berkeley, University of San Francisco, and UCSF as well. Each speaker is going to spend about 10 minutes discussing the Nobel Prize, and then if we could save questions till the very end, and then you can ask a question on any topic at the very end. Okay, with that, let me introduce our first speaker, which will be discussing physics, Aparna Venkateswaran. Hopefully I didn't say that too badly. She's in the Department of Astronomy and Physics. She obtained her PhD from the University of Chicago in astronomy and astrophysics. She currently teaches physics and astrophysics at the University of San Francisco. And her research is mainly in theoretical cosmology and high-energy astrophysics. Please have a warm welcome for Aparna.
Well, good evening. I know it's asking a lot for a weeknight for people to just come out and hear about this. I'm very grateful to see all these smiling faces, especially some of my students. And I do want to thank USF, Ludwig, and Valerie for organizing this event. I also want to acknowledge John Ruppel for his help in putting together some of the slides, and also thank some of my former mentors at the University of Chicago, where a lot of these particle physics discoveries laid the groundwork for this discovery. Okay, so the 2013 Nobel Prize in Physics was awarded for the discovery of the Higgs boson. So this image here shows the front and back of the metal, which actually is similar for several fields, including physics and chemistry. But I'll later explain the inscription, the translation, in just a couple of minutes. The right is just a picture I took of our lovely church. Venus is kind of shining between the towers there. But again, I want to give you a quick overview. Here is the actual citation, and I won't read through that because that's just tedious. But this is the actual citation, but it was awarded jointly to Francois Englert from Belgium and Peter Higgs from the UK, from England, for the discovery of this mechanism, essentially the Higgs mechanism that I will explain, that contributes to our understanding of a variety of particle physics and astronomical phenomena. Now, these two discoveries were proposed independently almost 50 years ago in 1964. And the award came to them, like I said, just this year in 2013. So that's just something to keep in mind, that it's fortunate these two gentlemen are still around. They're both in their 80s because the Nobel Prize is not awarded posthumously. So partly, their co-discovery, and partly that they're here, and the timing was right because the Higgs boson was just discovered last year by CERN, which I'll now talk about. So again, this is an image, an actual still of some of the particle tracks from CERN and its instruments that led to the discovery of the Higgs boson in July 2012. Okay, so I'm sorry, I'm just trying to operate off several computers here because of how things have been set up. All right, so I want to now explain several things so you can understand the significance of this event. I'd like to talk to you about what a boson is, and then also what is a Higgs boson, and what is that about, okay? So a boson, the very term boson is in acknowledgement of the contribution of an Indian physicist, Satyendranath Bose, almost a century ago, who worked along with Einstein to propose a class of particles that had integer spin. In fact, he worked on something that has come to be known as Bose-Einstein statistics. Now, the boson itself is a particle that has integer spin. So quantum mechanics says that particles, elementary particles, have a number of properties, one of which is their intrinsic spin. And by integer, I mean whole numbers, 0, 1, 2, I mean it like that, okay? The role of bosons in our universe is to mediate the interactions between the particles that make up the matter in our universe. And those particles are called fermions, after Enrico Fermi. And fermions have half integer spin, so I mean half, 3 halves, and so on. So, okay, so there's the particles that make up matter, fermions, and then there's the particles that mediate those interactions, that mediate the forces, the 4 basic forces in our universe. So that's what a boson is. Now, what is the Higgs boson, and how big is it? I'll get a little bit into the Higgs mechanism and the Higgs field in just a minute. But the Higgs boson has a fairly large mass. It took a little while to discover it because of this reason. In fact, much of the groundwork was laid down at Fermilab, at the Tevatron, and a number of other experiments in the decades leading up to its final discovery. But the Higgs boson mass is in units of, and I'm just I'll pull this up here. This little unit here, the GeV per c squared, think of that as a poor man's gram. It is a particle physics unit of mass, but think of it as a poor man grams, because 1 GeV per c squared is very close to the proton's mass. So this particle is about 127 times the proton's mass, and it is very, very fleeting in its existence. Very fleeting. How fleeting? It's a tiny fraction of a second, 10 to the minus 25 seconds. So the way we discover it is to smash proton beams that are accelerated to almost the speed of light, and we catch it in the act of passing through in the interactions that follow when you smash these proton beams together. Okay, so that is how we find it. Okay, so moving on then. Here now, I have actually listed the expansion and translation of the quote on the back of the Nobel medal. It actually translates to something like, and they bettered life through their art or their mastery of their work. Okay, so I want to give you a little bit of a broader context. What is the significance of this discovery? Why do we care? After all, we live in a universe that has a perfect zoo of elementary particles. Why do we care about this one? Well, this was one of the last missing pieces in our explanation of all the particles and fields that exist in our universe. This is the so-called standard model of physics. And many of the early particles proposed by it, the 3 families of light particles or leptons, their partnering neutrinos, the families of particles that live out there, and how everybody has a antimatter buddy or a supersymmetric buddy. That whole theory was contained in the standard model and in extensions in the supersymmetric standard model. This was one of the last particles left to be discovered. So its discovery is big. It's really, really big. The significance also, there's a lot of significance, not just for physics, but for astronomy and cosmology. Essentially, the Higgs boson is mediating and is expressing a background energy field in the universe known as the Higgs field. And when particles interact with this field, they gain mass. Okay, so perhaps you have thought about, why do some things in the universe have mass, but other things don't? You know, light photons mediate the electromagnetic force, but they don't have mass. Whereas other particles that mediate forces or other particles in fermion groups have mass. So why is that? Through interactions with this background energy field, the Higgs field, of which the Higgs boson is an expression. Okay, so again, essentially, particles in our universe acquire mass through this. So it is literally the dream that stuff is made of. I hope I said that right instead of the stuff that dreams are made of. This is an elusive dream, right? It's around for 10 to the minus 25 seconds. So it's an elusive dream that stuff is made of. Okay. Secondly, there's a lot of ramifications of this. I'll just mention a couple more in passing. There's a lot of implications for supersymmetry models, also for our four basic forces in the universe, weak and strong nuclear forces, electromagnetic, and gravity. There are some very strong implications from this discovery for the unification of the electromagnetic and the weak nuclear force. Something that's been proposed for a long time has been partially confirmed, but now this provides great confirmation. There's also a lot of implications for the origin of the universe and a phase of accelerated expansion called inflation in the first second of the universe, as well as the eventual fate of the universe. So there's a lot of implications there. Now, I think putting this all together and taking a broader humanity-based view, I think in some sense this also validates answering big questions through big endeavors, big experiments. And I'm not just saying this to get funding from our House or Senate. I really mean this in a big way, that sometimes it really takes, in this case, tens of thousands of people working over a decade from over 100 participating institutions and many dozen countries to get to this. So I know the Nobel Prize went to these two gentlemen, but really it's been this collective humanity effort. It really has been. Also very cool, we really are seeing how the physics of the ultra-small affects the fate of the ultra-large. I mean, we're really talking the fate of the universe, the origin of mass, things that are happening on billions of light years over many, many hundreds of billions of years, but because of these tiny particles on the tiniest scales. Okay? And I want to just say just a brief last point about just a philosophical aside. This was a relatively linear, untroubled trajectory from prediction to discovery to award. And some people have had some humorous asides about it on the Huffington Post or otherwise, talking about that. This was a discovery that confirmed things, but we're still hoping for more good stuff from it. The Large Hadron Collider is now closed for 2 years just to rest up and upgrade. But when it reopens, we're hoping that it'll have follow-up discoveries, including follow-up data on the Higgs boson, that'll shake up our view more, because that's what we're really looking for, not just confirmation, but what have we missed? What is the shake-up, and so on. Okay, we're looking for that. There are some examples of that, but if people want to ask me, I can come back to that. So again, one example of something that really shook up our worldview was the discovery of neutrinos' oscillations and their mass in 2002. That really was an enormous surprise, and people had to go back and redo their work. But again, these are some of the broader takeaway points that I'd like to leave you with today. And to wrap up, as we look ahead, I'd like to leave you with some just takeaway points looking ahead, what kind of discoveries you can expect in the next 5 to 10 years that will be impacted by this. Maybe some of you have heard about how neutrinos are no longer massless as we used to think they were. Neutrinos are an elementary particle that we used to think traveled at the speed of light and had no mass. But now we realize that they have a trace amount of mass. And that discovery is coming in the next decade, and it will be impacted by what we find out about the Higgs, because it impacts what kind of particles exist in our universe. Many other related discoveries, even on dark matter and on dark energy, those models will be influenced. All the missing unseen components of our universe will be affected, again, by this discovery of the Higgs boson. And I want to conclude with a slightly bittersweet note, but maybe just laying down some hope for the future of U.S. physics and science. Now, 1993, when I began graduate school, was the year that a very, very big particle physics experiment, the superconducting super collider in Texas, was shut down. $2 billion were invested in it from funding. The tunnels were partly built underground, but then Congress slowly took away its funding, and that was the end of that story. But it would have gone up to 5 times as much energy and been bigger than CERN. But unfortunately, that's not the way it worked out. And so slowly, the discoveries in particle physics have moved abroad. And similarly, in many areas of astrophysics, including dark energy, slowly, many of the missions are moving from the U.S. to abroad. So I hope that we come back to funding many of these basic physics, which many U.S. physicists and astronomers have laid the groundwork for. And I hope, for humanity's sake, that we see many more of these great discoveries. So thank you.
Thank you very much, Aparna. Okay, our next prize is the Peace Prize. I guess that's a big prize. Stephen Zunes, Professor Stephen Zunes, will present that. He's from the Department of Politics. He obtained his PhD from Cornell University in government. He currently teaches the politics of war and peace, U.S. foreign policy, and global conflict resolution at the University of San Francisco. His research is in the field of conflict resolution, and he has written many books, book reviews, published papers, chapters, and my printer ran out of paper printing his resume. Would you please welcome Professor Stephen Zunes?
Thank you. There's been a Nobel Peace Prize is one of the most closely watched of the Nobel Prizes, in part because of its political implications. Some years it has gone, to activists, to grassroots organizers who have, risked a lot for the cause of justice. Many people had hoped that Malala, the young Pakistani girl who'd been barely survived a Taliban attack, would be there. Other years, it has been government officials, many of whom had been warring for many years to decide to make peace. And this is the source of some of the more ironic peace prizes to people like Henry Kissinger, Yasser Arafat, Menachem Begin, among others. But there's been increasing attention to international organizations, including those that have been going, subjected sometimes to criticism. And this was an effort, I think, in part to say, hey, yes, despite the problems some of these organizations have had, they serve a purpose. They are making a difference, and they should be honored. Now, the organization for the prohibition of chemical weapons is the implementing body of the Chemical Weapons Convention, which was originally came together in 1993 and was entered into force in 1997. And it has 4 key provisions: destroying all existing chemical weapons under international verification. Now, the use of chemical weapons has been banned since 1923 in the conference that came after the horror of World War I, where there's widespread usage of chemical weapons. And there have been isolated uses of it since then by Mussolini's forces in Ethiopia in the 1930s, by Egyptian forces in Yemen in the 1960s. The worst case, of course, was that of Saddam Hussein's forces in the 1980s, both against Iranian troops and against Kurdish civilians. And then, of course, we've had the more recent horror of the use of chemical weapons by the Syrian regime. But it was recognized that it wasn't good enough just to ban their use. That even though in many ways it's played an important role. For example, in all the horror done by all various sides in World War II, they were never ever used during that conflict. That the total elimination really was necessary to rid the world of that threat. This also involves monitoring the chemical industry, to prevent new weapons, from emerging, and providing assistance and protection to states parties to the conflicts against chemical threats. That is, so they don't have the excuse, well, we need to have these because our enemy might have them. And fostering international cooperation to strengthen implementation of the convention and to promote the peaceful uses of chemistry. The 189 states are part of this treaty. It works as a fairly small, works a relatively small staff out of their office in The Hague, but they've had remarkable successes. They've overseen the elimination of 80% of the world's chemical arsenals over the past 2 decades, and they are well on their way to eliminating most of those. And though the award emphasized what they have done so far, they've been in the news recently because they made possible the avoidance of war on Syria. Indeed, the fact that President Obama, after announcing an intention of U.S. military intervention in retaliation of the Syrian regime's chemical weapons attacks, the fact that there was a diplomatic alternative was critically important in avoiding that. I personally, as those of you who've known about my work in terms of Syria, I've been a long-standing critic of the Assad regime and the horror unfolding there, but I personally think going to war would have made things worse instead of better. So, like a lot of people, I was relieved that there was indeed this option, though it doesn't address the underlying horror that is still going on there. At least this element can be addressed peacefully, and I think more effectively than war. Another reason I think they got the prize is that it emphasized the importance of universality in disarmament efforts, rather than targeting specific states for geopolitical reasons. Indeed, the great powers have sometimes been criticized for targeting governments they don't like and I suppose the governments we like. I mean, there's been a lot of attention, obviously, on Iran's nuclear program and their violation of UN Security Council resolutions and trying to get them to stop the reprocessing of nuclear fuel that has the potential of enabling them to create nuclear weapons in the future. Yet Pakistan and India and Israel, which already have nuclear arsenals, are also violating a series of UN Security Council resolutions regarding their nuclear programs, and yet the U.S. has blocked the UN from enforcing sanctions and other actions. Indeed, Israel, along with Egypt, which I mentioned actually has used chemical weapons back in the 1960s. They are, they have chemical weapons arsenals. There's not been much pressure there, but this idea that I think the name, giving them the prize, saying, hey, if disarmament of any kind is going to work, it needs to be universal. It can't be based on what the United States or Britain or France or Russia or some other great power says most important. But again, universality is critical. And again, it challenges the notion that unilateral military action against alleged chemical weapons possessing countries is the best means of dealing with these dangerous weapons. We saw how, of course, that the Iraq's alleged chemical weapons arsenal, which they in fact had eliminated 10 years earlier, was used for an excuse, a major excuse for the U.S. invasion of Iraq. In many ways, just to underscore this last point about universality versus unilateralism, the first Director General of the OPCW was José Bostani. He is a Brazilian diplomat, and under his leadership, the number of signatories of the treaty grew from 87 to 145, which is the fastest growth of any international organization that I'm aware of. And they oversaw the instruction of 2 million chemical weapons, about 2/3 of the world's chemical weapons facilities. And he was reelected unanimously in May of 2000 for another 5-year term. Secretary of State Powell referred to him for his very impressive work. And the Guardian referred to him as a workaholic who'd done more in the past 5 years to promote world peace than anyone. And yet, he was the United States successful in getting him fired in 2002 First they tried to get the Brazilian government to recall him, and that didn't work. They tried to get a vote of no confidence at the UN. That didn't work. And they began putting pressure on some of the UN's weaker countries, and basically said the U.S. would stop funding its share for the OPCW. It was about 22% of the budget, which would really hurt their efforts. And a plurality of nations agreed that it's better to get rid of Bustani than to lose that funding. I should say, incidentally, that the UN Council, the ILO, the highest administrative panel, later ruled that this was, in fact, an illegal firing. Apparently, what they're upset about Bustani was that he wanted to inspect U.S. Chemical weapons facilities with the same rigor that they were inspecting others. But the thing that really got us upset was that he was trying to make a deal with Saddam Hussein that would allow the OPCW to come to Iraq and inspect their potential chemical weapons facility, which would be separate from UNSCOM, which had a lot of problems in terms of violating their mandate in terms of wiretaps and spying and stuff, and they thought through a universal model they might be able to cooperate, and of course the Bush administration knew if the OPCW did that and they got to Iraq and discovered they didn't actually have chemical weapons after all, it would eliminate one of the major rationales for the invasion. So they got rid of him there. But I'm using this just as an example to kind of underscore that I think the part of the political motivation, frankly, for this award was challenging. Was pushing the idea of universality in disarmament efforts instead of singling out a particular country. Now there are some real challenges right now that's facing the organization. The first, of course, is overseeing the destruction of serious chemical weapons. Now that's always a complicated task, but they obviously have had a lot of experience, and they're very good at it. But this is the first time they try to do such a thing during wartime, and there's a pretty good idea of where these weapons are. The idea is to get them in one place and either try to disarm them there, or maybe fly them out of the country to a secure location. And begin the dismantling process there. Sometimes it's challenging, but the initial reports is that it's going surprisingly well. That people are hopeful. They are working on a one-year deadline. That may be a little over-optimistic, but again, they seem to be making progress. Another problem is the two largest stockpiles. That is, in Russia and the United States, are years behind the deadline for total elimination. The original deadline was 2007. There was an special extension given to 2012, but now it looks like we're looking like 2022 before these arsenals will be completely eliminated. As far as you can tell, they're not. Neither Russia nor the United States are cheating or avoiding their responsibility. It's largely logistical and technical. But again, these arsenals are so huge compared to others. It's still an issue. Our arsenals currently are located in military bases in Kentucky and in Colorado. And perhaps the biggest challenge of all is getting the remaining non-member states to join. And that's Israel, Egypt, North Korea, Burma, Angola, and South Sudan. The first three of which do have chemical arsenals, and that is still very much of a challenge. Again, given that these are the recalcitrant nature of North Korea, as what I think a lot of people would see as a rogue state, and the fact that Egypt and Israel have powerful allies, and in terms of the United States, that has thus far resisted efforts to pressure those countries or condition aid to their joining the treaty. Thank you.
Thank you very much. Now we are at the Chemistry Prize, and we are fortunate enough to have Professor Teresa Head Gordon from UC Berkeley here. She is in the Department of Chemistry, Bioengineering, and Chemical and Biomolecular Engineering. She's basically taken over the campus. She obtained her PhD from Carnegie Mellon University in theoretical chemistry. She currently teaches biophysical chemistry and bioengineering at UC Berkeley. Her research encompasses the development of general computation and experimental methodologies applied to biology, biochemistry, and biophysics. She has published over 100 papers and presented over 100 seminars. Please give a warm welcome for Teresa.
Thank you very much. It's nice to be here. I'm glad to be able to sort of actually present another face of chemistry, which is a little more favorable one. And so we'll begin with the fact that the 2013 Nobel Prize in Chemistry was awarded to these three fellows. And I actually know these three guys reasonably well. Martin Karplus is actually considered to be my academic grandfather. But I have great affection for him for the reason that he's actually a really well-known gourmand. And so in addition to spending time at Harvard, he has also spent sort of the last half of his career in Strasbourg in France, where he essentially worked with some of the best chefs in France. And the reason I have sort of great affection for him is that one of the two times that I've been to Chez Panisse was at his invitation. So when he came to visit Berkeley, I was able to go to Chez Panisse. Michael Levitt, actually, we got stuck at a NSF workshop in Texas where we were pretty much the only people in our area. So we hung out in Texas together, which was quite fun. And he's a very kind and optimistic person, very gentle person, someone who's very enjoyable to be with. And then Arya Warshall is a very difficult person, but actually quite a visionary. And so the thing that I sort of kind of like to sort of say that he earns it honestly, which is that when he actually served as a soldier in the 7-Day War, and going out on an operation with his outfit, his entire unit was killed except for him. And so I've interacted with Arya, and I always sort of remember that story when he's being difficult. Okay? All right, so I thought I would start with a quote for this area, which is that the quote is actually from Auguste Comte, and he was a terrible prognosticator of essentially successes in science. He's notorious for this, I'm afraid. And what he says is that every attempt to employ mathematical methods in the study of chemical questions must be considered profoundly irrational and contrary to the spirit of chemistry. If mathematical analysis should ever hold a place in chemistry, an aberration which is happily almost impossible, it would occasion a rapid and widespread degeneration of that science. Okay. So the thing is that he was, but to be fair, that was 100 years before we actually understood the atomic, structure of materials. And this essentially was then summarized roughly 100 years later by Dirac, who said, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty lies only in the fact that the exact application of these laws leads to equations much too complicated to be soluble. And so that essentially is the crux of essentially kind of the progression that I'd like to take you through that leads to the 2013 Nobel Prize in Chemistry. It actually began in 1967 at the Weizmann Institute. And if we didn't have this this rule that you have to be alive for the Nobel Chemistry, in addition to these three fellows, certainly someone who might have replaced one of them would have been Shinar Lifson. And so Shinar essentially was one of the sort of leading physicists, or chemical physicists at the time, who was developing approximations to quantum physics. And he had the young Arya Warshall has a PhD student, and then Michael Levitt was actually waiting to go to Cambridge University in the UK to start his PhD studies. And they didn't have an opening in the particular year that he wanted to, so he was left. He had to spend a year in Israel, where he was essentially a very talented computer programmer. And what they did was they essentially developed some computer codes that they actually put on a machine that they called the golem. And the golem is essentially from Jewish folklore, which is essentially an animate being that's actually made out of inanimate material. And so the beginning was there, and then Arya decided to go do a postdoc with Martin Karplus. in 1969. And there they essentially started putting all these pieces together. And now what I'd like to do is to essentially describe how, so having told you how these people came together, what were the pieces that they actually put together that eventually led to roughly, 35 years later, the Nobel Prize. Okay, so there's a little bit of confusion about what we mean by, what they won the Nobel Prize for. And so we'll start with quantum physics, and really what Dirac was referring to was the solution to the Schrödinger equation. So that's the mathematical equation which was understood, and what Dirac said is that what the complexity of it is essentially, of solving it in an analytical form is a non-starter. And so therefore you got to take it to computers, and you have to, when you put it on a computer, you have to approximate it. And so what I'm showing here is the Schrödinger equation on the bottom there. And you can see that there's this H with a little hat on top of it, and essentially that's called an operator, Hamiltonian operator, and it's composed of the kinetic energy of the nuclei and the electrons, as well as the potential energy of how the nuclei interact with each other, nuclei and electrons, and then all of the complexity actually in solving this equation is how electrons talk to each other. And that is inherently quantum mechanical. The way we describe these electrons are through something called the wave function. And so this nature, that sort of how we describe that wave function involves essentially approximations of how we describe the electron-electron interactions. So what I'm showing you on the y-axis is essentially, do I have a pointer? On the y-axis, is there a pointer? Okay. Oh, it's running out of battery. Okay, let's try it. Let's try here. Okay, so what we have here on the y-axis is essentially the level of approximation to this electron-electron interaction. So this so-called full CI approximation is pretty much exact. But the nature of those equations are so complex that we can only solve that for a couple of atoms. All right? And so then as we essentially march down and we get more and more approximate, we eventually get to something called density functional theory, which allows me sort of to take this out into sort of on the order of 100 to maybe 1,000 atoms, okay, to describe those electron-electron interactions. And that sort of practicality of essentially, first of all, the density functional theory approximation to Schrödinger's equation was why Walter Kahn won the 1998 Nobel Prize in Chemistry. And then John Popel was essentially a popularizer of these other techniques that are so-called wave function-based methods, and the fact that he wrote a very popular computer program to solve those. Now, the problem with this, the problem here is that really what I would like to be able to do is I would like to be able to describe the energy, okay, by solving the Schrödinger equation of this position of all the nuclear degrees of freedom of all the atoms. Now to essentially change. Okay, so then we essentially have the positions of all the atoms, and that essentially puts us onto another area of the potential energy surface, which involves a value of the energy. And so think about this as a sort of a topographical map. Okay, so this is, for example, the Grand Canyon. And I'm sort of sitting at the bottom of the canyon, and if I want to move up, okay, uphill, okay, to reach the top, then I essentially have to change my position. And when I change my position, the nature of my potential energy changes. And therefore, think about this sort of this molecular space as being very much like trying to climb out of the Grand Canyon. And when I do that, which is that what costs so much is that every time I change my nuclear configurations, I have to solve this equation again. And what I'm trying to show here is that this gets to be very expensive. So there's two things that I couldn't do until these other three came along. Was the fact that I wanted to be able to evaluate the energies for big molecules, okay, something beyond 1,000 atoms. So I can give you many examples: proteins, nucleic acids, materials of all sorts involve hundreds of thousands, if not millions and millions of atoms. All right, so the thing is that what they were able to do then was to take this quantum physics approach and actually replace it with a classical physics approximation. And what this would allow them to do was to, first of all, to be able to do big molecules, and actually be able to also take how big molecules actually change their conformations in time. Okay, so the first thing they were able to do is to approximate now a new level of theory, which got rid of the electrons, integrated out the electrons, leaving behind just how effectively the nuclei move under the classical approximation. All right. And then what they combined it with was classical mechanics, which is the idea that not only do I want to, first of all, now do, millions of atoms, I also want to be able to follow how those nuclear positions change in time. And so this is essentially called statistical mechanical averaging. If you look here, which is that by simplifying this, it goes into this equation, and what these integrals tell you is essentially all the possible positions of the atoms, okay, that where every positions of the atom, every time we change them, we have to evaluate a new potential energy value to know how important that conformation is. Okay, so that's really what they did, was to first of all provide an approximation, okay, to the quantum physics, and then to essentially move in time with classical mechanics. Okay, now Michael Levitt made the observation that none of this would have been possible. The 1998 Nobel Prize in Chemistry would not have been possible, nor the 2013 without the invention of computers. And so you could argue that maybe Gordon Moore, who was the co-founder of Intel, might have been, a possible share of the prize due to the fact that he was, of course, sort of actively involved in the creation of computer chips. And what he did was he actually made an observation in 1965 in an obscure journal that the compute power of the computers were going to double every 2 years, because the density of which you could actually build features onto the computer chip were also doubling every 2 years. Okay, so here's what we're seeing here. In 1975, you have about 29,000 transistors. Those are the nature of those little features that are needed to improve computational speed. In 1995, we're up to 5.5 million. In 2008, we're about to 2 billion. Okay, so the idea was that this was called Moore's Law, and it was actually held out to very recently. And so we're essentially working on new technologies to overcome this. But the idea was that in order to solve these very complicated chemical equations, one needed computers to go along with it. And so the golden age of computing came along right at the right time in order for that to advance. Okay, now what can you do with this? So now you've got the theoretical foundations and you've got the hardware, computer hardware. And it's sort of kind of floating around at the time was our first, essentially, nuclear positions of big molecules. And so the advent of Xray crystallography began taking off in the late 50s, early 60s, and the Nobel Prize in Chemistry in 1962 was the discovery of how to essentially determine the structure of big molecules like hemoglobin. So this is actually hemoglobin here. Dorothy Hodgkin actually won it 2 years later in 1964. And here what she was essentially taking those same techniques and determining that for very biologically important molecules like insulin. All right, so the idea is that look at that. So that's essentially this is a ribbon structure, and as you move along these ribbons, what you're doing is you're essentially following the geometric backbone of these big molecules, and so they fold up into these beautiful shapes. And this is what carries oxygen, okay, in your blood, this hemoglobin. And when you look at it, it looks really static, right? It's just sitting there. It's just sitting there with just not moving its nuclear positions. But what we know is that in fact it does move. And so what was really important about the 2013 Chemistry Nobel Prize was the fact that they were able to take these energy models and to simulate them in time to generate these kinds of motions to actually understand how these actually biological, these large molecules actually functioned. And so these are sort of this combination of computers and chemistry were very important. Then the thing is that it's become kind of standard, really, honestly, in disease and understanding disease. And so what I'm showing here is now the hemoglobin molecule, which are those dimers come to form together to form trimers. Those are big red spots. This is essentially the binding of oxygen right here. Okay, and this is what gets transported in your bloodstream, okay, to essentially be able to carry oxygen to different parts of your body. Now, what happens in sickle cell anemia is that there's a single point mutation, okay, and so this is actually what happens now is that the disease state means that these hemoglobins go on to aggregate, and they aggregate into these very ordered structurals, which are called fibrils, which we're seeing here. And essentially, we now have a very good molecular understanding of that disease process, and something as important as sickle cell anemia, very similar things to what we see in Alzheimer's. Okay, so like I said, which is that the drug industry has utilized this. Is actually taken from one of sort of our drug industry partners that essentially are showing the chemical, taking how biological molecules might take sort of a strand of DNA and essentially cut it up. And so that sort of making and breaking of chemical bonds requires us to go back and actually combine quantum physics and classical physics. This is where I thought the Nobel Prize Committee actually kind of misunderstood, which is that this is something that certainly the 2013 Nobel Prize winners laid down the foundation but had not really solved. In fact, we're really far from solving. So a very strong possibility that this could be the subject of a future Nobel Prize, which is really how to really make this work between the quantum and the classical. Okay. I thought I would just sort of end by thanking Ludwig for organizing this. And I just wanted to say that the 2013 Chemistry Prize, as Martin Karpla said, consecrated the field. And having worked in the field, I really felt really happy that day when it was awarded. You kind of feel consecrated yourself. And so, anyways, thank you very much for listening.
Thank you very much. Our next topic is medicine. And to present is Jason Fernandez. He's an adjunct professor in the biology department of USF, and he's also a postdoc at UCSF in the Department of Biochemistry and Biophysics. He received his PhD from UCSF. He currently teaches biology, and his research focus is on host-virus interactions and viral evolution of HIV-1. Would you please give a warm welcome for Jason Fernandez?
So I'm going to be talking today about the Nobel Prize in Physiology or Medicine, and I think one of the important things to note is the title of this Nobel. There is no Nobel Prize in biology. So that means typically biologists win either the chemistry prize or the medicine prize. And so this year, the medicine prize went to a lot of basic biology. And the three winners were James Rockman at Yale, Randy Schekman across the bay at Berkeley, and then Thomas Sudoff down the peninsula at Stanford. And the Nobel Committee cited their work in discoveries of machinery regulating vesicle traffic, a major transport system in our cells. So if that sounds like a little complex to you, this is the important word. This is really the traffic. This is really the traffic Nobel. So they basically figured out sort of the mass transit system of our cell. So before we get to actually into the science of this Nobel, let's just talk about who got left out, because as other presenters have noted, there's this crazy rule of three. Only 3 people can win the Nobel. And the most notable omission is Richard Scheller, currently at Genentech. There's another prize known as the Lasker Prize. A lot of people call it the mini Nobel, and most people win the Lasker before they win the Nobel. And Dr. Scheller has shared the Lasker with some of the gentlemen beforehand, and he could easily have been plugged in, and one of them left out. And unfortunately, he sort of missed his shot at the Nobel because this work has now been awarded a Nobel. So he is really the most glaring omission. And then on a lighter note, one of my good friends actually works in Dr. Shekman's lab, and Dr. Shekman is quite known for his mustache. And this is a picture of their lab the day Dr. Shekman received the call that he won the Nobel, and they all put on mustaches to kind of congratulate him, but his mustache did not actually share a portion of the award. my sort of favorite story from that morning is that they were, Dr. Shekman they were filming a lot of him sort of, how did you feel when you got the call and whatnot. And so then he walked into his lab and he happened to meet one of his graduate students on the elevator, and his graduate student wasn't really expecting a full camera crew and stuff to jump into the elevator with him. And so he kind of had to make conversation. He said, "Oh, congratulations, Randy. Have you got your parking spot yet?" Because those of you who know anything about UC know that once you win a Nobel Prize, the real prize is you get free parking for life. And so if you ever go around Berkeley or around UCSF, you may see these spots that have an NL on them, and you need an NL permit, which means Nobel laureate. So, that's the real reward here. But let's get to the actual science. So, if we think about a cell is really just a bag of water, but it's a compartmentalized bag of water. So, there are all these. If you remember back to high school biology, you'll know that a cell has a nucleus. It has a lot of other substructures we call organelles. But information has to move from one compartment to another. So one of the really fundamental questions in biology is, how does information move from one compartment to another? And then how does it move from one cell to another, right? When you get hit on the knee, how does your brain actually process that information and say, hey, I've been hit on the knee, right? How does that information move throughout the body? And this is such an important question in biology that it's actually already received a Nobel for. The 1999 Nobel was awarded because we had already known that there are these little bubbles, these blue bubbles that move around in a cell, and they're called vesicles, and they carry cargo. But Günter Blobel had actually done some work, which I'll discuss on the next slide, sort of getting at how this vesicular trafficking, so this is how the mass transit system of the cell works, how some of the details of that. And then these three gentlemen sort of furthered that work. So this is Dr. Blobel's work on the 1999 Nobel. So if we kind of draw the analogy between the mass transit system of the cell and, let's say, San Francisco mass transit, what Dr. Blobel discovered was that certain cargo in a cell contains a signal sequence on it that kind of determines its destination. So it's kind of like if you get on the bus or you get on the train and you see the sign that says, okay, this is the end, it's headed to the Caltrain depot, you know you're going to the Caltrain depot. You don't know how long it's going to take you. You never know how long Muni is going to take, right? You don't know who's getting on with you. You don't know the route you're taking, but you know you're going to end up at the Caltrain depot. And so that's what he discovered. And then these three gentlemen came in. So first was Dr. Schekman, and what he wanted to know is, imagine you're this alien coming to San Francisco to study the transit system. The first thing you want to do is sort of figure out, well, what are the agencies involved, right? And if there's going to be stuff like the SFMTA, there's going to be Muni, there's going to be the Department of Public Transportation. They're all going to be involved. But there are going to be other departments like the Parks and Recreation Department, those things that you're going to want to rule out. So he's going to use genetic approaches to say, hey, what's involved in mass transit in the cell and what's not. Dr. Rockman is going to take a different approach. He's going to say, if I wanted to build a mass transit system in a test tube, what would I need? And so he's going to try mixing and matching things. He's going to take a very biochemical approach. This is classic biochemistry. And then Dr. Sudoff is going to come along a little later, and he's going to say, okay, now that we're starting to understand this transit system, I want to understand how the doors know when to open and close. Why aren't we just spilling our cargo all over the cell? Why aren't they just randomly opening and closing? You may have seen a couple Muni trains do that. It's not a good thing, right? So let's start with Dr. Shekman. So what Dr. Shekman does, he works in yeast, okay? So, but a lot of this is going to translate to higher order organisms. And so what he does is he has these yeast that he knocks a single gene out of the yeast. And this is actually one of the advantages of working with yeast. This is fairly simple to do. And so you have your normal yeast, and it has its normal, remember these blue bubbles are vesicles, so they're doing their thing, transporting cargo around. But a couple genes, times he'll knock out a gene, and he'll see defective transport. So now all the blue bubbles are accumulating. They can't bud out to another cell. They're just stuck, and you see all this aberrant vesicular trafficking. And so from that, he's able to say, okay, well, this mutant was mutated in a certain gene. I knew what that was. And he generates a list of genes that are involved in this secretion pathway. And he calls them Sec1, Sec2, and he finds 23 genes. And then what he does, he says, okay, now that I have these players, now that I know, Muni is an agency involved, and I know the N-train is an entity involved, I want to now organize them. So I want to know that the N, and I want to know that the J and the T are all part of Muni. And I want to know that, BART is a separate entity. So he starts mapping these in different pathways. And at this point, he's aware of Dr. Rothman's work, so this is where there's going to start to be some synergy between them in terms of categorizing these. But let's turn to what Dr. Rothman's doing concurrently while Dr. Shekman's doing that. So he takes a different approach. So he's going to actually work in animal cells, and he's going to infect those cells with a virus. And the reason he does that is that the virus is very easy to identify, and the virus is going to use the vesicles, right? The virus is essentially going to get onto the mass transit system of our cell and move around. And so now that he has a very easy to identify thing, a viral protein, he's just going to kind of pull that down and then see what's attached to that. Because if the virus is riding on a immunity train, if you just kind of see what's around it, you'll start to see, maybe, if we take it a bus, you might grab the wheel of a bus, and then you say, okay, you want to find the rest of the bus, so you keep pulling, and if you pull on the wheel, then you'll get the rest of the bus, you'll get the overhead wire and whatnot. So that's his approach. So he, pulls down the viral protein, and he finds this human protein called NSF. And coincidentally, this is one of the same genes. So remember, he's working in animal cells, but it's also one of the same products that Schekman's also found in yeast. So all of a sudden, we're seeing a lot of intersection between their work. So he finds NSF, so he's found the wheel of the bus. He says, what's attached to the wheel? And then he finds these, he actually calls them NSF attachment proteins, or SNAPs. And he says, okay, now I found more of the bus. What's attached to that? And then he finds these receptors for the SNAPs, and he calls them snares. And so now he has a pretty good picture of what the actual bus is, and he can actually assemble it in a test tube. And there's a complicated, for any biology majors, you've probably seen this sort of stuff before. So now we have this model where, we know that there are these snaps and these snares, and they've got to stick together, and then cargo comes out. But Dr. Sudoff's wondering, well, if all this stuff is always present in the cell, why doesn't it all just fit together and then all the cargo spill out all the time? And he's especially interested in this because he's not necessarily thinking about just yeast cells. He's thinking about actual neurons, which are going to use the same sort of mass transit system. And if you think about neurons, you might remember that they release neurotransmitters across the synapse, right? So when you get hit in the knee, there's some signal in your brain that's, getting that signal by neurotransmitters being released from one cell to another. But clearly, you're not always thinking that someone's hitting you in the knee. So usually that signal is off. So why is that? There's got to be some door keeping the cargo inside the bus. And so he finds this gene, and it's actually also one of Shekman's genes, that's acting as a gate. It's keeping the doors. These are the doors. They're keeping the vesicle closed. And he's now working in mice. So he notices that mice that have this gene mutated actually lose the ability to secrete neurotransmitters. And then, now we know what the doors are, but how do the doors know when to open and close, right? That's the big question. So he also finds this other gene. It's called synaptotagmin 1, and it acts similar. It interacts with these snares that Dr. Rockman found. So once again, synergy between these laureates. And he finds that the trigger is a calcium ion. So the calcium ion is telling the doors when to open and close, which is kind of a mind-boggling thing, right? To think that part of any thought you have is in part due to some calcium ions just moving around, right? That's a very important step. So he's able to find the trigger in that way. So if we take this all together, it's a very simple model. This is not entirely accurate, but it's just here for simplicity's sake. If you have your cargo vesicle, you have your vesicle carrying important cargo, say a neurotransmitter. You might have these two snares. This is the compartment it wants to get into, and there's a gate keeping it closed. But if you add calcium, the snares are able to bind, the snap is able to bind, and all your cargo gets unloaded into the compartment. So you might be saying, okay, this seems really cool, but who really cares? What does this mean in the big picture? And these findings have allowed actually a lot of really cool applications to come to light. So 1/3 of the world's insulin is currently secreted in yeast, okay? And this is all because Dr. Shekman was able to actually figure out how secretion works in yeast. And then he said, now that we know how to do that, let's make the yeast secrete something that we can actually use. So rather than having to, isolate, pig insulin or some of the other things people used to do, we can now actually make human insulin in yeast and then just collect it because the yeast spit it out. And in fact, the entirety of the world's hepatitis B vaccine is generated in part using methods similar to that. As Dr. Rothman's own work showed, he used a virus to sort of address these questions. Viruses are hijacking these pathways. So if we understand these pathways better, we know how better to target them with therapeutics. And then lastly, Dr. Sudhoff's work, like I said, is kind of mind-boggling when you think this is how, communication across your body, this is how thoughts and sort of sensations, how you experience them, is all due in part to these findings. So it's really kind of mind-boggling. But then in big red letters, I kind of want to sort of end on this note, and I think all three Nobel laureates in their public statements have been very clear on this, is that, one of the great things about their work is that these are just basic science findings that contribute to just our understanding of how life works. And all three have said they're very worried that if they were starting their careers out now and applying and proposing the same grants that eventually won them the Nobel Prize now, they wouldn't actually be funded, because we're very much in a translational atmosphere. People want to know, how are you going to cure cancer? How are you going to cure HIV? Not, I'm going to figure out how secretion works and I'm going to study it in yeast, right? That doesn't sound as exciting, but the basic science is what lets you build cool applications. And you can't possibly predict that a third of the world's insulin, the entirety of HPV vaccines are going to be made until you know how secretion works. So that's why basic science is very important, and it was very nice to see a Nobel go to basic science. So this work has really been long overdue in being recognized, and was definitely well deserved.
Our next prize is for literature, and Professor Dean Rader will be speaking about that. He's in the Department of English at USF. He received his PhD from the State University of New York in comparative literature, where he also studied creating writing and translation. He is currently teaching English and creative writing at USF. He is an avid poet and has won numerous awards for poetry and written several books. He has edited a curious anthology of poems for the 99%. It's called 99 Poems for the 99%. Please give a warm welcome to Dean Rader.
Well, thanks to Ludwig and Valerie for organizing this. It's a lot of fun to be here. The Nobel Prize for Literature is a weird animal. There's one person, right? As you've seen, there's a lot of collaboration. There's controversy in these other areas because you can only name three. There's one author who wins every year. And as you've seen, there tend to be certain kinds of people who work at certain kinds of places that win the prize in the other disciplines and the sciences. So many at U of Chicago and Berkeley that you get your own parking spot, right? I mean, there tends to be locations. That's not the case with literature. You can imagine, every country in the world, emerging countries, so-called third world countries, first world countries, any place that humans write, people are writing. And then you not only have, fiction writers, but poets and dramatists and essayists. It's a crapshoot who's going to win the literature prize every year. And writers and scholars have a lot of fun handicapping who's going to win. There's these computer programs. You can play Nobel literature candidate drinking games. You can assemble a potential Nobel laureate fantasy team. And, based on that, you might win or lose. The Nobel Prize in Literature is curious. It was one of the original 5 prizes that Alfred Nobel endowed in his will. And the language that he used is also interesting. Alfred Nobel said that he was going to award work, quote, in the field of literature, the most outstanding work in an ideal direction. And that phrase, ideal direction, has been translated differently by the committee over time. Early on, it was translated it's like this notion of perfection. And so some of the greatest writers, people like James Joyce, Henry James, Nabokov, they didn't win the Nobel Prize because people thought that their work was maybe too realistic, and didn't really sort of promote an ideal. And over time, that language has been interpreted a little more liberally. The winner this year is one of the most curious winners in decades. The Canadian short story writer Alice Munro, and the citation was this: Master of the Contemporary Short Story. And that's really all she's done. Literally, all she's done is written short stories. One of the only fiction writers that I can think of that's won the Nobel Prize that's never written a novel. She's written 14 collections of short stories, all of which are set in her area of Canada, Western Ontario. She's never really written about politics. She has stayed out of politics herself. She doesn't really write about social issues. Issues of race and class don't really enter into her work very much. She writes a lot about gender. She writes a lot about women. She writes a lot about the relationships between women and men. And she's interested in the interior lives of women and men. She writes a lot about small towns. She writes a lot about gossip. She writes a lot about secrets. I think one of the most interesting things she writes about is the social pressures of secrets. In fact, one of her books is called Open Secrets. And she's very interested in what the external pressures of a small town can do to the internal life of an individual. A lot of her narrators are first-person narrators, and most often the narrators in these stories confess something to the audience, to the reader. She was born in the 30s. In Canada. She published her first short story as a student in her university literary magazine, so I always encourage my students, start somewhere. The Ignatian, USF's literary magazine, publish your first poem there, and, 60 years later you might win a Nobel Prize. You cannot start too small. And no one started smaller. And no one's work has been less seemingly ambitious in scope. It's so strange for someone to hold so steadfastly, so completely to one genre, but she did. She kept resisting the urge to write the big novel, to go for the big project. And in the past, most of the Nobel literature laureates have been those writers who have written like a trilogy of novels or spent their entire life, mining some project. And so if you think of most Nobel Prize winners as sort of going for the macro, Alice Munro has rather unsexily stayed with the micro. And most writers are pleased with her win. She's maintained her residence in a small town. She teaches, now and then, here and there. She talks a lot about issues of craft. She's notorious for writing short stories, publishing them in the New Yorker. She published her first New Yorker short story in the 70s. I'm thinking that's one reason she won the Nobel Prize. She's been a favorite of the New Yorker for 30 years now. She writes long short stories, and they tend to look inward. She will revise a short story dozens and dozens of times before it gets published in a magazine, revise it again before it gets published in the Canadian version of her short stories, revises the stories again before they get published in the version that appears in the UK, and then will often revise them again before they come out in the US. And then she will revise them again before they get published in like a collected stories. Sometimes she will go through and change the narrator from first person to third person. She will take out some of the drama, add in some drama. This is, I think, a kind of typical passage from her work. Always remember that when a man goes out of the room, he leaves everything in it behind. When a woman goes out, she carries everything that happened in that room along with her. In your life, there are a few places, or maybe only the one place where something happened. And then there are all the other places. That's from one of her stories, Too Much Happiness. This is from a couple passages from a short story called Runaway. This is what happens. You put it away for a little while, and now and again you look in the closet for something else, and you remember, and you think, soon. And one of the things I would encourage you to notice here is how the speaker is addressing you, the reader. There's a kind of intimacy in these works, these stories that are a little bit of confession, in which you feel like the characters in these short stories are divulging something to you. And there's this really intimate connection that happens. Then it becomes the thing that was your bright treasure. You don't think about it. A loss you could not contemplate at one time, and now it becomes something you can barely remember. This is what happens. Few people, very few, have a treasure. And if you do, you must hang on to it. You must not let yourself be waylaid and have it taken from you. So this notion of looking at how people communicate with each other and how we as individuals keep something interior is the basic thrust of her work. I've been asked if there's one work that I would recommend. I would look at her 2008 book. It's called something like The Best of Alice Munro. And it's her favorite short stories that she's published out of the 14 collections over the years. Thanks.
And now we're at our final prize. It's the Economics Nobel Prize. Our speaker is Professor Jesse Attila-Hughes. He's in the Department of Economics at University of San Francisco. He obtained his PhD in Sustainable Development from Columbia University. He teaches microeconomics and natural resources and development. His research includes the global climate's long and short influences on human capital, tropical cyclones and infant mortality, and financial market responses to advances in climate science. Please give a warm welcome for Jesse.
Hey, everybody. Thank you, first of all, for organizing. This is a very cool event. I'm enjoying it very much. One thing that I do want to say is it's late. I know, so I'm going to try and keep this fast, almost economical, if you will. But the one thing that I should say before going on is you might have seen the star there. Yes, the Nobel Prize in Economics is a little bit different from the other Nobel Prizes in that it's not actually a Nobel Prize. By which I mean it's actually the Sverige Riksbank Prize in Economic Sciences in memory of Alfred Nobel. So it was actually commemorated in 68 or started in 68 at the 300th anniversary of the bank's founding. It was not in Alfred Nobel's original will. And so this is sort of an interesting thing to think about. You know, economics gets a lot of flack, sometimes very justly, for not being a science, and sometimes very unjustly. There's actually a really nice op-ed in the Times today by Raj Chetty, who's an economist at Harvard, who is utterly brilliant, about the fact that at least some parts of economics really, really do hew very closely to science. Other parts, I know that Professor Emeritus Fisher, who's a macroeconomist, has left, so now I can safely say that macro, maybe not so much. But in general, this has become, this is sort of a generalized social science prize now. And it's so not strictly given to economists. We've had a couple of poli-sci professors, Daniel Kahneman, who actually also in The Economist last week had a very nice sort of counter article about the trouble with science being sufficiently objective these days. So just to keep that in mind before we go on. So this year's Economics Nobel was given to Eugene Fama, Lars Hansen, and Robert Shiller. For their empirical analysis of asset prices. So this is going to be a finance Nobel. And this is from the original press release. Right? There's no way to predict the price of stocks and bonds over the next few days or weeks, but it is quite possible to foresee the broad course of these prices over longer periods, such as the next 3 to 5 years. These findings, which might seem both surprising and contradictory, were made and analyzed by this year's laureates. And so what is this prize about? Really, this prize is about figuring out how we end up with prices for assets, right? And what's an asset? Here, we can think about this in a very generalized sense. But here we're showing the price over time of the S&P 500, which is a composite index that's chosen by Standard & Poor's, sort of the top 500, if you will, or however you want to think about it, companies being traded in the United States. And so we look at something like this, and this has not been adjusted for inflation, so it looks like, it's even more so than you would normally think so in terms of growing. But you think, okay, so how does this price move around? When, why? And we can't get too much into sort of what a price is, right? But in a lot of ways, we can think of price as, it is a signal. It's the information about something's value, right? And so in the end, this is pretty foundational research. I really liked, your claim at the end about, the need for funding basic research. This is very much sort of foundational research into how markets work. And as a result, it's interesting to sort of look at the contrast between these three guys. So Eugene Fama is at UChicago, right? So UChicago is sort of classically the most, we'll get a rap sometimes for being too pro-market, but UChicago is this very strong set of theorists and a long history of people who really, really understand, the sort of very interesting equilibrium properties of markets. And what he's most famous for is the efficient markets hypothesis, which in essence shows that in general, behavior of financial securities, stocks and bonds, basically anything that's traded, is very, very difficult to predict, right? And it's a nice kind of background story on this, in the sense that Eugene Fama actually first started thinking about this when he was an undergrad. Again, the importance of starting young, right? And he was working in a stock brokerage trying to come up with trading strategies, and none of them really worked. And after a while, he's like, I don't really think that trading strategies in general work that well. Maybe there's something generalizable about this. And it turns out there is, right? So basically what Eugene Fama is best known for is the idea that, over relatively short periods of time for any given security, it's very difficult to predict the path of the security. In essence, all the information that's currently available to society, public information, right, and this sort of the simplest way of thinking about this, right, is already incorporated in the stock's price. So you can't come up with sort of simple rules to figure, the stock is going to go up and then it's going to go down and it's going to look like a head and we're going to look at this on a chart and this is what it's going to look like. And, today, it depends on what news station you watch, but we forget that not too long ago, this is kind of how people thought about stock prices. They would do all these sort of convoluted charting exercises in X and Y and Z and really not get necessarily that far with it. So this is, he ended up sort of coming up with, it's almost paradoxical when you think about the fact that he was best known for efficient markets. He also is most famous, probably after that, for Fama-French factor model, which is sort of a way of understanding the generalized motion of stocks as a function of how the market moves and a couple of other factors related to sort of, the size of the stock relative to other stocks. And so in a lot of ways, you can look at what Eugene Fama did, and you can almost think of this as a pain to the fact that markets are going to, in general, be efficient. You're not going to be able to cheat your way into getting some kind of amazing returns off of your stocks because everybody else is trying to do it at the same time. Sort of correlated to that is almost as an aside, Eugene Fama sort of started the event study literature, which is now a major part of finance, related to how we think about how stock prices tell us about, how good a certain event was for a certain company. The second guy here is a particularly interesting pick. He's a particularly interesting pick to try to explain to a general audience because it is a very, very technical pick. So Lars Hansen is also at Chicago, I believe in the business school. And he's famous for an econometric technique. So econometrics is this specific brand of statistics that economists use. And he's famous for developing the generalized method of moments. And the tie-in to the rest of the prize is that this specific econometric technique is what you use to test the efficiency of markets. You use it for a variety of things in economics, depending on sort of the structure of the statistical problem that you're working on. But in general, that's kind of how it ties in. To understand it without using any math, or without using any math in numbers or figures. In essence, what GMM lets you do, or generalized method of moments lets you do, is test relatively complicated hypotheses that require a whole bunch of different conditions to be met, right? And to do so in a way that is efficient in the sort of colloquial sense, by which I mean speedy, and in a precise way. And this is important, when we think of the advances in computing that allowed so much research to come down the line. This is sort of this important intermediate step back when we had really, really strong limitations on our computing power. The fact that GMM was so efficient was a really, really big advance. Big advantage over previous techniques. And the last of the laureates here is Robert Shiller, who's at Yale. You can kind of think of Shiller as being, in some ways, almost the opposite of Fama, in the sense that, Fama is famous for is sort of, the fact that in the short run you can't really do anything to predict which way stock prices are going to go. That's one way of thinking about it, right? Shiller, on the other hand, is a major figure in behavioral finance. So he's done a variety of work on sort of speculative bubbles, inefficient pricing, and sort of irrational behavior of markets, if you will. I think he's best known for showing that the volatility of stock prices is significantly greater than the volatility of dividend payouts. And if you think that, stocks are supposed to be these forward-looking things that are efficiently traded, this is not something you would expect. He's probably also, of the three, the most famous outside of academia, right? So he's famous, for one thing, for being one of the earliest predictors of the U.S. housing bubble and financial crisis. And I should, not to get too much economist inside baseball here, but Fama famously said that Shiller has been predicting that since 1996, so the extent to which the prediction is solid, well, sorry, that was mostly for you. But so he's famous for sort of being the naysayer that, yes, well, markets can behave very efficiently in the short run, no dig on Fama there, but in the long run, you can have all kinds of crazy behavior that emerges from these sort of aggregate properties of humans buying and selling things, or selling computers to buy and sell things. He's also very famous for the Case-Shiller Home Price Index, which was one of the things that he helped use to figure out that there was a housing bubble coming, right? So it's kind of funny to think that up until relatively recently, and economics sort of faces the same funny constraints that all the other areas of research do, and sometimes we're like, wow, we didn't have those data before. So Shiller was one of the first guys to come up with time series data on home sales for geographic units of area. So basically, you could track housing prices at a representative sample across the entire United States, or for up to 20 different metropolitan areas. Here we see it for San Francisco. Actually, the U.S. one doesn't look terribly different. And so you can see there's the housing bubble that made Shiller famous, if you will. And then the collapse in the housing market that came around, 07, 08. And then, the financial crisis that ensues. So to sort of think about what this Nobel means, right? Financial markets are efficient, but don't always act, rationally. I'm putting rationally in quotes because rational means something very specific in economics. But rationally in the sort of colloquial sense, by which we mean, yes, markets will be very efficient in the sense that you can't necessarily go out there and say, oh, I'm pretty sure that this stock is undervalued and I'm going to be able to just follow this strategy and make some money, right? You're competing against everybody else in a large market, and in general, public information isn't going to be something that you can trade off of. But that doesn't mean that in the aggregate, you can't sometimes end up with very funny market behaviors. And thus, so we have these sort of two guys on opposite ends of the spectrum talking about very different parts of the market in very, very different ways, and coming to, it actually turns out, some rather different policy conclusions depending on, who asked them when and what scope. Despite the fact that I would say in a lot of ways each of their discoveries really isn't that at odds. And then we have the sort of econometrician in the middle that provided the technical platform that let us all go forward. And if you want to read more about it, and I don't know if you guys get the slides afterwards, that's a whole bunch of things sort of running down the laureates themselves. So thank you guys very much.
Thank you very much. I wanted to add one point that you mentioned, that Fama says he's been predicting these prices since 96. In 2005, when he predicted the housing, so did many other people, including myself. This wasn't something very complicated. I shorted housing in 2005, lost all the money. Shorted housing in 2006, lost all the money. Shorted housing in 2007, lost all my money. 2008, I was fed up, I didn't do it, and that was the year to do it. So it's a good point that you make about Fama, that even though these models say there's predictability, trying to make money from it is really difficult. Okay, well, I want to thank all the speakers because that was really wonderful. I learned a lot. And now we'll open it to questions to the audience. Ask any question that comes to your mind in any of these fields.
Question for Aparna. I heard someone on one of the radio programs that the Higgs boson is somehow evident when we turn on our computers. Is there any... I think I remember someone saying that as simple as when you turn on your computer, something happens that is related to the Higgs boson. Is there any, do you know of anything related to that?
Gosh, I can't say I do. I'm trying to think of the implications or ramifications of what it's sort of a mass lending mechanism. It's, I suppose... Yeah, I'm not sure about that, but certainly come find me. Let me think about that, and we can continue the conversation. I have heard when you turn on your television, you're still catching a bit of the Big Bang, the microwave radiation left over from the Big Bang today in the microwave is there, but I have not heard that about the Higgs boson. Yeah, thank you.
So one of the questions is, does someone or an organization need to be nominated for a prize, or do they just apply for it?
They're nominated for it. They don't apply for it. even though some do lobby to win the Nobel Prize. But typically, people in the field will write nominating letters, and so they don't essentially apply.
Is there any prize money for each category?
Yes. I off the top of my head, it's like $1.2 million is 1.2 million for each category. But then I think if it's a multiple awardee, you split the prize, correct? Yeah, you split. So it's 1.2 million per category, and then you split it if it's multiple awardees. So literature wins out.
And the last question we had was, is there a list of criteria that must be met for each category, and where would you go to find that out? So remember you said something about, for literature, most outstanding work in an ideal direction.
If you go to the Nobel's website, they have some information there. It's not extremely detailed, though, but there's some basic information on their website. Nobelprize.org, I think it is.
In the economics category, and this probably also applies to chemistry and physics, but most specifically in economics, these three winners, do they work in conjunction in order to, I guess, come up with a theory that allow them to win the Nobel Prize? Or they do separate work on their own and somehow it just comes together at some point? I don't understand.
Yeah, so I think it depends on each prize in each category in each year, right? So in the chemistry prize this year, there was, those guys all kind of worked together and were in and out of the same labs. Fama and Schiller famously don't really get along that well and kind of often will say contradictory things, and never really work together. And so in the case of the economics prize this year, it's sort of, you can think about it as this is very foundational research into why and how markets operate. And sort of at one end of the scale, like in the sort of short run, they're very, very efficient. They do a really, really good job of, incorporating information. But at the other end, you can have all these kind of weird behaviors that deviate from that. And it was really discovered by two guys who didn't even really like each other that much. But the Nobel Committee looked at that and said, despite the fact these guys haven't worked together, they're part of this sort of cohesive whole advancement, right? And you can't really look at one and honor one without honoring the other. That's kind of how I think a lot of times they'll put these prizes together.
I had another question for the gentleman about the Nobel Prize in Medicine. I called in to Michael Krasny's show when the professors from Stanford and Berkeley were on the show. And I pointed out that Robert Reich has said that in regards to basic research, money for basic research, they seem to be complaining, almost whining. And I said, I think that scientists need to get out in the street. Robert Reich has said the only time that America has changed when dirty air, dirty water, thousands of people got out in the streets. And they didn't complain. They got out and demonstrated and raised holy and unholy hell. And it seems to me that scientists and social scientists need to get out in the streets and get their students and their lab assistants, and because a lot of us are looking for leaders. We know that there needs to be change in this world because corporations are not paying their taxes, rich people are not paying their taxes, and the professor from Berkeley even suggested that we should add an additional charge to the pharmacy products when the people are already paying outrageous prices as it is. So my concern is I'd like to see scientists and organize once every 6 months or once a month demonstrations in front of these companies that don't pay any taxes, that should be paying the taxes, to pay for the basic research. Yeah, and he agreed with me.
Yeah, so I think I would say that I think there definitely needs to be much better communication of how important basic research is. And I think that's events like this are sort of great in getting that idea out that, a very basic fundamental knowledge about how yeast secretion works actually has an impact in how you may, in the pricing of, in making your insulin cheaper and higher quality. That said, I think, having an award for that is very basic research will sort of help increase the publicity of that sort of thing. And, in terms of taxes and costs, that's always a tough question. I think we definitely need to be moving towards communicating better that basic research is actually leading to great applications, and then people can understand how that's actually affecting their lives and get more passionate about that.
I have a question for you, actually.
Yeah.
You mentioned about, I believe it was Shekman who did the insulin release.
Yeah.
And I thought that, I've always thought for years and years that was Genentech, their main invention that made them all the money.
Actually, no. So Genentech's main invention is human growth hormone, which, if you ever go down to the Mission Bay campus, you'll realize there was a lawsuit that names UCSF's main building Genentech Hall. But Randy Schekman has consulted for Chiron Corp. That's across the bay in Emeryville, I believe. And they were the ones who perfected insulin secretion. And that's actually been a huge boon. Before, I believe you had to mash up pig pancreas to get pig insulin. But now you can produce human insulin in yeast. And that's a much preferable and much cheaper way of doing things.